Hello, these are the lecture notes talking about Newton's laws for physics. So the first thing that we're going to do is do a quick review of Newton's first law, otherwise known as the law of inertia. Essentially, the law of inertia states that unless there is a net force, an object will continue with a constant velocity and therefore zero acceleration. So if the net force is zero, the object could be moving, it could be stationary. Either way, there is no acceleration. We call this a state of equilibrium. Equal literally meaning that the forces going in all directions are equal or canceling out. With that, let's take a look at some examples. Here we have two different cars, a Maserati Gran Turismo S and a Volkswagen Beetle from 1971. They're both on a straight test track, and the Maserati is going at a constant speed of 250 kilometers per hour, while the Beetle goes at a constant speed of 75 kilometers per hour. Which car has the greater net force? Well, the key here is it's asking about net force. Since both of these are going at a constant speed, that means that acceleration is zero, right? Because velocity is constant. So, if the acceleration is zero, that must mean that the net force is also zero for both vehicles. Therefore, neither car has a greater net force. They both have the same. And again, that's because they're going at a constant speed. In a different type of example, one that you might be familiar with, a school bus comes to a sudden stop, and all of the backpacks on the floor slide forward. What force is causing them to do that? So let's draw a quick little picture. Here is a chair in a school bus. Here's the ground. Here's a bag. So initially, they're moving to the right. So let's say V naught is greater than 0. After the bus slides to a stop, the chair is not moving, but the backpack continues to move. Why is that? So the reason why does not have anything really to do with force. When the bus stops, the backpack continues on. Why? Because of Newton's first law. Its inertia is causing the bag to continue in its path of motion, and the only thing that's going to stop it from doing so is a force. So inertia actually carries this forward, and it doesn't carry it like a force carries something. It carries it forward essentially as a tendency to resist changing. This is similar to what you feel if you stop in a car very suddenly, or even if you turn in a car. What you're feeling is essentially inertia carrying you forward and some force applying to you in order to stop you or turn you. So again, what's important here is that inertia is not a force, and it does mean that objects will try to continue whatever motion they have unless an extra force acts on them. With that said, let's start talking about what happens if you actually have some forces acting on an object. This gets us to what we would probably term as the most important of Newton's laws that we use most frequently, and that is Newton's second law, that states whenever you have an unbalanced set of forces or you have an overall net force, your object will accelerate proportional to its mass. So right here we have Newton's second law, and you'll notice that they have the little arrows here. That just means that this is a vector. So the force is a vector, the acceleration is a vector, because the direction of those variables matter. The direction of the applied or net force will affect the direction of its acceleration, which makes sense. If you push forward on something, that object should be accelerating in the forward direction. So similar to what we did a long time ago with vectors, we will spend a little bit of time separating it into x and y components in order to deal with these types of forces where you have two dimensions in our problem. So the overall important thing to know here is Newton's second law is typically just remembered as F equals ma. So let's take a look at how this law works. So to do that, let's take some estimates for how much force, so net force in this case, is needed to accelerate two different things. First is a 1,000 kilogram car at 1/2 g. So let's go ahead and set this up in a good problem-solving style, where we say that our mass is 1,000 kilograms, and our acceleration is equal to 1/2 g. And if you recall, g is approximately 10, or you can use 9.8. Let's use 9.8 this time, so that our acceleration is actually 4.9, and that's again meters per second squared. So what net force is needed for this? Well, in order to figure that out, we need to use Newton's second law. So the net force is equal to mass times acceleration. So in this case, we would have 1,000 kilograms multiplied by our 4.9 meters per second squared. So multiplying these two together, we would have 4.9 times 1,000, which is 490. And the units are a little weird because we have kilograms times meters per second squared. Hopefully you remember that kilograms times meters per second squared is what we call a Newton, because that is our SI unit of force. So let's go ahead and take a look at our apple. So our apple is a little different because the mass is 200 grams. Now that's a problem, because in order to use newtons, we need kilograms. So let's restate this as 0.200 kilograms, because a kilogram is 1,000 grams. The acceleration, it says, is the same, so we're going to use the 4.9 that we used in the previous part. And we still want to know the net force in order to cause this acceleration of the apple. So again, we do the same process. The net force is equal to the mass times acceleration, which in this case is now 0.2 times 4.9. And so, in this case, excuse me, our net force is going to be 0.98, and that's going to be newtons. So you can see that to cause the same acceleration for two different masses, you have very different forces. 490 newtons for a large car versus less than a newton for a small apple. Now let's do a slightly more complex problem. In this case, we want to know what force is required to stop a car, on average, when it's going 100 kilometers per hour after a distance of 55 meters. So in order to do this, I'm going to write out my information. So V naught is 100 kilometers per hour. And I did a little research ahead of time and calculated that this is approximately 27.8 meters per second, because I'd like to be in meters and seconds. I know that the distance that I travel here, the displacement, is 55 meters. I know that my final velocity is 0, but I don't know the acceleration of my car. This right here represents one of our kinematic problems that we've done previously. So this, in conjunction with the fact that I know the mass is 1,500 kilograms, should help me figure out the force acting on the car. But first I need to do kinematics. So I have V naught, delta x, v, and a, which points me to the third kinematic equation, which if you recall is v squared equals v naught squared plus 2 times a times delta x. And in this case, final velocity is 0. So I can just go ahead and say that's 0. So if I rearrange this and solve for a, I would have negative v naught squared on the left side, 2a delta x on the right, and then I would divide both sides by 2 delta x. So that on the right hand, the 2's cancel and the delta x cancels, leaving me only acceleration. So this here is my substitution part. So I'm going to have negative 27.8 meters per second squared over 2 times 55. So plug that into your calculator and you find that your acceleration is about negative 7 meters per second squared. So we used kinematics to calculate our acceleration. Now we can use Newton's second law to calculate the net force on our car. So Newton's second law, remember, says the net force is equal to mass times acceleration. So in this case, my net force would be equal to 1,500 times my acceleration of negative 7 meters per second squared. So when I plug this into my calculator, I find that my net force has to be actually negative 10,500 newtons, and if you were to round that, you would get negative 11,000. And so the reason that our answer here was negative 11,000 is simply because I only had 2 digits in my original numbers. So it wasn't very precise, so I did a lot of rounding for my final answer. So what to take away from this is, sometimes you will have to use kinematics to find the acceleration in order to use Newton's second law. And that's okay because kinematics really is just solving a kinematic equation. To follow up our longer problem, we now have an easy problem. So if I have a constant horizontal force with a magnitude of 20 newtons on a box that has a mass of 40 kilograms on a level floor, so that just means that I'm talking about a box that looks like this, where I'm applying a force. What is the acceleration of this box? So I'm going to write out my knowns. So my mass was 40 kilograms. I know that the force applied to it is 20 newtons, and I want to know the acceleration. So in this case, I'm going to start with Newton's second law. F equals ma, and I want to know the acceleration. So in order to solve for acceleration, I'm going to divide both sides by the mass, so that you see the mass cancels on the right-hand side, leaving me with just acceleration is the force on something divided by its mass. In this case, then, my acceleration would be 20 newtons divided by 40 kilograms, so that my acceleration would be only 0.5, and my units would be meters per second squared. And I know my units will be meters per second squared because I was dealing with newtons and kilograms, which are SI units. All right, after that breather of an easy question, let's go back to one that involves kinematics once again. So now I have a ketchup bottle with a mass of 0.45 kilograms that is pushed to the right along a smooth counter. So let's draw a ketchup bottle on a counter, and it moves initially at 2.8 meters per second to the right. Then it slows down because the countertop has friction, and it slides for a whole meter before it stops. So over here, its velocity is 0. So what is the magnitude and direction of this friction force that slows the bottle down to a stop? So let's write out our information. V naught is 2.8 meters per second. V final is 0. I know that my displacement is 1 meter, but I don't know my acceleration, just like the previous question. I also know that the mass is 0.45 kilograms, but I don't need that until I figure out the acceleration. So let's do that first. So just like the previous problem, we have a kinematic equation that has all 4 of these variables, which is the third kinematic equation, v squared equals v naught squared plus 2a delta x. And so you can actually solve this again the exact same way, or you can look back at your previous problem to find that the acceleration would be equal to negative v naught squared over 2 times delta x. So substituting here, I would have negative 2.8 squared over 2 times 1, which is pretty easy to calculate. Put that in your calculator and you get an acceleration of negative 3.92 meters per second squared. And now we can go on to calculate our net force. So here's my mass. So my net force, I'll do it right here, is equal to mass times acceleration. So in this case, I would have my mass of 0.45 kilograms times my acceleration of negative 3.92. And so putting this in, you end up with something that is pretty darn close to negative 1.8 newtons. Now you'll notice that in my answer here, I said that it's 1.8 newtons to the left. And that makes sense because if I am traveling to the right, my friction force is going to be to the left because it is resisting this ketchup bottle's motion.